Hi everyone. In this video series I'm going to introduce you to two-level multi-level regression modeling, and we're going to be using the Jamovi program. Jamovi is a freely downloadable software at the site that you see on the screen. And I will include a link to it underneath the video description. So the reason why I've chosen the program is that it is extremely intuitive and easy to use, and multi-level regression modeling can be somewhat complicated at times even without having to struggle with programming. So that's essentially why I've chosen Jamovi, is to make it simpler to actually carry out analyses and comprehend the concepts. Now for our demonstration, we will be analyzing data from the high school and beyond data set from 1982, and I've downloaded this data set from the Mayor Tools package in R, and the data set contains data on 7,185 students that are nested within 160 schools. And basically the models are intended to predict student math achievement as a function of student level predictors and school level predictors. So I am going to make a copy of the SPSS data file available as a download underneath the video description. Just so you know, Jamovi can import SPSS data files, so there's no problem with that. You should be able to import it very easily. Also, for similar presentations using data from the high school and beyond studies, you can see Heck et al.'s book, Multi-Level and Longitudinal Modeling with IBM SPSS, and Pittock and Stevens' treatment of this data, or this type of data, in their book Applied Multivariate Statistics for the Social Sciences. A lot of the coverage or discussions are in this particular presentation are going to pivot off of notation and some concepts related to Heck et al.'s presentation, even though the data sets that I'm working with and what they worked with appear to be somewhat different. Finally, let me note that as we're going through this particular video series, I'm going to be working from this PowerPoint that you see on screen. I will make this PowerPoint available for download underneath the video description, so be sure to go there for that as well. The PowerPoint is just going to contain a lot more information than I can really cover in the video series. So it is pretty comprehensive. It includes a reference page at the end if you want to look at that as well. So let's go ahead and get started. So the general scenario is that we are studying student level and school level predictors of student scores on a standardized measure of math achievement. So math achievement is going to be a level 1 outcome, and we're going to be including student socioeconomic status as a level 1 predictor, as well as the mean school SES as a level 2 predictor, along with school level predictors of school type, which is coded 0 for public school, 1 for private school, and the size of the school, which is basically measured as the number of students attending. So the models that we will analyze in this series: first we will test a null model with no predictors, but allowing intercepts to randomly vary. Second, we will test a model that includes the level 1 variable, student socioeconomic status, as a predictor of math achievement. Third, we will test a model that includes the level 2 predictor, mean SES, as a predictor of variation in school level intercepts. Fourth, we will add in additional level 2 predictors of variation in intercepts. And this is going to include our school type and our school size variables. And then fifth, we're going to test for and probe we're going to actually test for random slopes, and then also probe for possible cross-level interactions. So here I've opened up the Jamovi program and imported the data, and so you can see we have a number of variables in here. So essentially, again, we're going to be predicting students' math achievement scores as a function of student level and school level predictors. So math achievement, you'll notice this is the variable that we're going to be trying to predict. And in the data set, you'll notice first off there's a student identifier. We're not really going to be working with that, but basically each row in the data set is a case related to a given student. We have a variable that is school ID, and so this is an identifier for the school within which a student resides, if you will. So you'll notice that all the students within a given school will have the same school identifier. We're not really going to be working with these two variables here, so I'm just going to move on to SES right here. And so this is the student level socioeconomic status. And you'll notice that within schools, you'll see that there's variation in socioeconomic status. So that's our level 1 predictor right there. The level 2 predictors will include school size, the school type variable, which is coded 0 for public and 1 for private, and then mean SES right here. So you'll notice that essentially the size of the schools, we have the same value for all those students within the same school. We have the school type, the same value for as well. So basically all of the level 2 variables will be constant for students within their respective schools. So for the first model that we're going to test, it's basically an unconditional or null model. So what this means is that basically we don't have any predictors that are included at level 1 or level 2. And we have equations that are laid out for each level of the data hierarchy. So we have a level 1 equation and a level 2 equation. So the level 1 equation essentially is modeling variation within schools on the outcome variable, and the level 2 equation is reflecting variation or trying to model variation between schools in terms of math achievement. So the level 1 equation, we have y subscript ij. So that's basically student I and school J's math achievement score. And we're basically saying at level 1 that it's a function of beta 0j, which is essentially the school intercept. And in this model where we have no predictors, the intercept is essentially just the mean for a given school with respect to math achievement. The epsilon ij is the residual at level 1, and that's just going to simply be the difference between the individual student score on y and the school mean with respect to math achievement. The level 2 equation, you can see that now we have our beta 0j set equal to gamma 00 plus mu 0j. So to make this a little less complicated, basically what we're saying is that a given school average math achievement score is equal to the grand mean of math achievement scores across all of the schools plus the difference between a school mean and the grand mean. So the grand mean, the gamma 00, is nothing more than just taking the school means for math achievement and then averaging them out, and that gets you the grand mean of that. Like I said, in this unconditional model with no predictors, the intercept is equal to essentially the mean for a given school. So we could talk about the gamma 00, and throughout much of our presentation we're going to refer to it as the grand mean of intercepts, but in effect we're really talking about essentially grand mean of means at the school level. So let's go ahead and get started. Oh, and by the way, notice too that this component is going to be important. This is reflecting the residual at level 1, or excuse me, at level 2. So essentially later on what we may do is, if we find that there are differences between schools, we may add in predictors of the variation in school intercepts or school means, basically identifying potential school level characteristics to predict that variation. So the last equation down here, you'll see we've essentially substituted our level 2 equation into the level 1 for the beta 0j, and so now you can see that we have each student score, each student I in school J is that their score on math achievement is equal to the grand mean of the school means, if you will, or the school level intercepts, plus the deviation between the intercept for a given school and the grand mean of those intercepts, plus the level 1 residual, which is what you see right here. A couple of other pieces of notation. We want to talk about the variance at level 1 and level 2. So in effect, we're for the unconditional model, what we're going to be doing is essentially estimating 3 parameters. So the first parameter is going to be the fixed effect related to the intercepts. So it's essentially going to be the grand mean of the intercepts across the schools. The other two parameters that are being estimated is the variance of the residuals at level 1. So remember that we had previously used the notation epsilon ij to designate a residual at level 1. So the variance of the residual throughout this presentation is going to be noted as sigma squared with a subscript of epsilon ij. The variance of the intercepts, remember that we were previously talking about the level 2 intercepts in terms of mu 0j for the residual error. Essentially then we can talk about the variance of the intercepts using sigma squared subscripted 0j. So going back to our data set, let's run our null model. So essentially what I'm going to do is I am going to click on linear models and click on mixed model. So when this opens up, whatever we do on the left side in terms of specifications and so forth, that it will be reflected on the right in our box on the right. So first off, what we want to do is to move our school variable down to the cluster variables box. And keep in mind that, we'll just go ahead and do this. We'll move it down, and then we're also going to move the math achievement variable to the dependent variable box. And next up, what we'll do is we'll scroll down, and you'll notice that we have REML selected for the estimation. So this is restricted maximum likelihood. So throughout the presentation in the PowerPoint, I'm using REML, but if we deselect this, then what we would get is maximum likelihood estimation. So I kind of talk a little bit in the PowerPoint about the difference between the two and when to use, but we're just going to keep this clicked for this demonstration. Next, we're going to go to random effects, and we're going to move this over to the box on the right. So it says intercept by school ID. And so when we do this, now what's going to happen is you can see that we get some real output right here. So you'll notice as we kind of look in the mixed models table right here, you've got model information. So we have general model information. We actually see that there's like a pseudo R-square that's given up here, and this is discussed a little bit in the PowerPoint, but we're not going to reference it too much in this particular video. Mainly what we're going to concentrate on down here where it says fixed effects parameter estimates, you can see that we have our gamma 0, 0, basically the grand mean of the intercepts across the schools. And so that grand mean for math achievement is 12.6. Over here you'll notice that we have a significance test that's given. So if we wanted to test whether the grand mean of the intercepts is significantly different from 0, then we have a test of that. Most of the time folks don't bother with that particular test, but it is there if you wanted it. Down below you'll notice that we have random coefficients table, and so basically it's broken out in this case into the level 1 variance term and level 2 variance term or variance component and the level 1 variance component. So these are the variances at level 2 and at level 1. So you can think about this first one right here. This is just basically our sigma squared mu 0j, and then this component right here is our sigma squared epsilon ij. Okay, so basically the idea, really the first decision that we're trying to make with the null model is whether or not it's even necessary to model the data using multi-level approach as opposed to a single level approach. So within a single level least squares regression, the basic idea, or one of the assumptions, is independence with respect to the residual errors. And so that basically means that we have residual errors that are randomly and independently sampled from a population of residual errors. And so what can happen though in certain natural settings or within certain survey designs, such as more complex two-stage surveys, is that we can end up with clustering of observations within groups or within higher level clusters. And this is manifest in observations on the dependent variable that are more similar within clusters and less similar across clusters. So practically speaking, in the context of least squares regression, because we make that assumption of independence, if there is a violation of that assumption and we don't account for it, then what that can translate into is a bias in the standard errors with respect to your regression parameters, and that can essentially translate into increased type 1 error possibilities when you're making inferences about population parameters. So the null model basically allows us to sort of ascertain whether this may be a problem if we were to use a single level regression modeling approach, and if there is evidence of significant clustering, then that would lend support for the use of a multi-level modeling strategy. So at any rate, what you'll notice right here with respect to there is actually a couple of ways in which we can ascertain whether there's substantial clustering in the data. One way is to test the variance component at level 2 right here. So we could actually test it using a likelihood ratio test. So in SPSS they actually use a wall test. Here we can actually select LRT for random effects, and this is a test of that variance component at level 2. So in other words, if we find that there's significant variation in the intercepts, then that would be an indication that we have substantial clustering or significant clustering going on. So basically the null hypothesis for this test is that the between group variability with respect to our intercepts is equal to 0, and so the alternative would be that the between group variability is greater than 0. And so you can see right here that with this test it is statistically significant, indicating that there's significant between group variability with respect to our intercepts. So that actually lends support for the use of multi-level regression modeling approach. Secondly, we have another indicator, which is the ICC. This is the intraclass correlation coefficient. And computationally, it's nothing more than just taking the variance of the intercepts at level 2, so the variance of our sigma squared subscripted mu 0j, and divide it by the variance of the intercepts again, mu 0j, plus the level 1 variance. So there's sigma squared epsilon ij. So in effect, it's nothing more than a ratio of between group variability to total variability. And so a value of 0 for the ICC would indicate that we have a situation where that there's no clustering going on, and values that are greater than 0 would indicate that we have more substantial amounts of clustering. Heck et al. In their textbook, they kind of describe a convention, usually around 0.05, as sort of a rough cutoff for determining more substantial levels of clustering. Just note that Pittick and Stevens, in their book, they kind of note that really any amount of clustering could be problematic with respect to the standard errors with respect to testing your regression parameters. So in this case right here, though, we see that the ICC is 0.180, so there's definitely evidence of substantial clustering that's taking place. So given our evidence of the clustering, we're going to stick with our multi-level regression model, and now we're going to add in a fixed level 1 predictor. So going back to our equations, our level 1 equation, you can see right here, now we've added in this beta 1j multiplied by SES ij. So the beta 1j is the fixed effect of SES, and that's being multiplied by each student I in school J's SES. So the level 1 equation is just basically stating that each person's math achievement is a function of the school level intercept plus the product of the regression slope for SES times each student's score on SES plus a residual. The level 2, now we have two equations. We still have our first equation as it was before with respect to our school level intercept. So again, it's just the school intercept is equal to the grand mean of the intercepts plus the deviation of the school intercept from the grand mean, or the difference between the two basically. And notice that now we've got this beta 1j set equal to gamma 10. So just kind of notice that essentially we could think about it this way, that if we were to compute the regression slope for SES, in all the schools and take the average, that is what the gamma 10 is. So just like we could compute a grand mean with respect to the intercept, we can also compute a grand mean for SES. Now notice that there is no random component associated with this particular coefficient at level 2. In theory, we could allow the slopes for SES to randomly vary, in which case we would add in a plus mu 1j. But in this particular demonstration right here, we're not going to include this. So we're just basically going to treat the slope as being equivalent across the schools. So through substitution of our level 2 equations into level 1, now we have each student's score in school J is equal to the grand mean of the intercepts plus the fixed effect for SES, which the regression slope is now the gamma 10, plus mu 0j. So again, that's the deviation, or the difference between the school level intercept and the grand mean, and then we have our level 1 residual right here. So this is the level 2 residual, this is the level 1 residual. Also note that within our model, the intercept, the school level intercept, is being adjusted for the presence of the SES predictor variable. So now let's incorporate SES into our model. So what we're going to do is we're going to go up here, move SES to the covariance box. And so when we do this, you can see that now SES is being added into the model right here. Let me note that by default in Jamovi, when we add in covariance, you'll see that it defaults using grand mean centering, and basically grand mean centering just entails taking SES and deviating it from the grand mean for the sample. And so what that translates into is that a new variable, a mean-centered variable that will have a mean of 0. You'll have positive values and negative values reflecting observations from the original variable that are falling above and below the mean respectively. The standard deviation for that variable, though, will be the same as the original variable. For this demonstration, I'm not going to use grand mean centering. I'm just going to stick with leaving it in its raw metric, none, right here. But you'll notice that there are various options with respect to centering our level 1 predictor. So we could do our grand mean centering. You have also the possibility of essentially a grand mean centering, but with a conversion to z-scores. So essentially taking those deviation scores from this step and dividing them by the standard deviation of SES, and that would convert it to z-scores. You also have cluster-based centered, which is essentially deviating SES raw scores on SES from the group means. So in that case, you would have essentially the mean SES within groups would be 0. And then but with the original standard deviation within the groups. And then you have cluster-based standardized, which is essentially z-scored within groups. Again, we're just going to leave it on none, but I do talk a little bit about centering at the end of the PowerPoint, so I'll leave that for you to review. So now, looking at our output, kind of scrolling down right here, you can see that we have our intercept, which is 12.66. And so that, again, that's the grand mean of the intercepts. Then we have SES, which is 2.39. So let me just kind of re-highlight this for us. 2.39, and so it's positive, and we have an indication of statistical significance. So what this is telling us is that students who scored higher on SES were predicted to have higher math achievement, and that's basically all there is to it. So with our random components right here, you can see our variance, our level 2 variance and our level 1 variance, both of those have decreased. We still see that the variance of the intercepts is statistically significant. So it may be that that we need to add in additional predictors, perhaps at level 1 or level 2, that would essentially account for more variation in the intercepts. A lot of times, if we find that there's significant variation in the intercepts, our attention generally is going to focus on level 2 predictors, more contextual level variables that may account for that variation. But given our non-centering, if you will, by adding an SES in this particular case, we basically have a situation where part of the relationship between SES and math achievement that is being modeled is also accounting for some of the between variation and that's contributing to the reduction at level 2. Nevertheless, we also see that our ICC is lower than it was previously. Now, I did want to mention that we can actually compute kind of an R-square-ish, kind of a pseudo R-square, using the variance components from the current model and the previous model. So the previous null model, we had this is the level 2 variance and then the level 1 variance right here. Our current model, this is the level 2 variance and level 1 variance right here. So we can talk about a reduction in the variance in the intercepts through the addition of the predictor. So it's essentially so essentially what that would translate into is taking, if we want to talk about the reduction in the variance of the intercepts, we would take 8.61, which you see right here, minus the 4.77 from the current model, and divide that difference by 8.61, which is the variance of the original null model. And so what we get is 0.445, which is basically an expression of the reduction in variance in terms of proportion of reduction. So we could basically say that the variance in the intercepts was reduced by about 44.5%. We can do the same thing with respect to our level 1 residuals as well. So we can just do that by taking the difference between our level 1 residual from our previous model and the level 1 residual from the current model, and dividing by that difference by the level 1 variance, which again is 39.15, and so what we find is that we get 0.054. So the level 1 residual is decreased by about 5.4%. So you can see that through the addition of the SES variable, it actually did a really nice job in terms of affecting the variation in the intercepts, but it didn't do quite the same job in terms of decreasing the within group variability, essentially at level 1. Now, for the third model in this particular video, what we're going to do is we're going to add in school level contextual variable, which is the mean SES variable. So as I said earlier, one of the things that we might be interested in is modeling essentially level 2 predictors of the variation in intercepts. So remember that the intercepts are essentially reflecting the school means, or in this case, because we have SES already in there, kind of a conditional mean, or the mean conditioned on the presence of that level 1 predictor. So we may want to look at school level factors that may be related to the differences that we observe across the schools. And so if we take the mean SES for the students within the schools, it may be that the mean SES may predict variation in the math achievement that we see at the school level. So our level 1 equation that you see right here is basically the same as what we had previously. Now, with our level 2 equations, we also have our fixed effect for SES at level 1 is exactly the same as before, but now we're incorporating a predictor, which is our mean SES variable. So in this case, we're trying to predict variation in the school level intercepts. So previously, when we didn't have the mean SES in the model, we were just basically simply saying, hey, there's variability in the school intercepts. Now we're trying to look at predictors of that variability by adding in predictors of the variability in the intercepts. So in this case, you'll see I have a gamma 0, 1 multiplied by x mean SES, basically for school J. Okay, so in terms of the subscripting right here, the gamma 0, 1, if I had multiple predictors, I would have a gamma 0, 2, gamma 0, 3, and so forth. So the 1, 2, and 3 respectively would be essentially denoting the predictor at that level for that particular coefficient. So if we substitute our level 2 equations into the level 1 equation, then we end up with this model right here. So let's go back to Jamovi, and we will move our mean SES variable over to the covariance box, which you see right here. And once again, when we scroll down, you'll notice that by default Jamovi has mean centered the level 2 predictor. So in this particular case, it's essentially just taking the average of the school mean SES variable and then deviating each school's mean SES from the grand mean of those. And just again, to keep this consistent with our presentation in the PowerPoint, I'm going to set this as none. Okay, so as we're looking at this, we can see again, there's our grand mean. This is our gamma 0, 0, which is the grand mean of the intercepts. Our SES predictor, or level 1 predictor, the fixed effect, the regression slope is 2.19, and we see that we have a positive and significant predictive relationship at level 1. Then at level 2, we have mean SES being positively and significantly predictive of math achievement at the school level. So basically, both SES at level 1 and mean SES at level 2 were both positive predictors of students' math achievement. If we go back down to our random components table right here, you can see that our variance estimate for the intercepts is decreased yet again, and so is the ICC. The level 1 residual has not really decreased a whole lot. And we also see that the test of the variance of the intercepts is still statistically significant. So again, we can potentially add in additional predictors at level 2 that might help to account for the variation in the intercepts. Once again, we can compute our pseudo R-squares by using the formula that I went over previously. So if we look at to find the reduction in variance at level 2, we can take the variance from our previous model with just SES included and subtract the variance from our model with including the mean SES variable, or the contextual variable, and then dividing that difference by our previous model for 4.77. So this is the formula right here. So we end up with 0.436. So in a nutshell, the intercepts the variance in intercepts decreased by about 43.6%. In terms of the level 1 reduction, we see that it only decreased, the variance at level 1 only decreased by about 0.02%. So as I said before, there wasn't much that was accounted for by adding in the predictors with respect to the level 1 variance. So at this point, I'm going to stop. The next video that I present is going to basically pick back up with model 4, where we are going to be adding in fixed level 2 predictors. Then we'll be testing a model where we have the slopes randomly varying, the level 1 slopes randomly varying, and then testing and probing potential cross-level interactions. So that concludes this video, and stay tuned for the next one.